Hello everyone. For those who don't know, because there's probably no one in the room, I'm Grahame Grieve. I'm the product director for FHIR. And loosely speaking, you can blame me for everything you don't like. Today I'm going to tell you about the FHIR mapping language, which is one portion of the FHIR specification, potentially one of the more challenging portions, and one that we're still seeing how it's going. So I'm going to talk to you about the FHIR mapping language, why we created a mapping language, what our goals are with that mapping language, then talk to you about how the mapping language works and go through a quick tutorial, and I'll look at some examples of its use. So everybody who implements at some stage needs to do mappings. Sometimes your implementation consists entirely of mapping, moving data wrangling from one format to another, and other times mapping's just part of what you do. So I suppose if you write a standalone application that uses a FHIR server as its data store and it's just a simple web client, maybe you haven't technically engaged in mapping. But there's not many of us who live in a world like that. We have existing data stores and existing data interactions, and we need to map. When I started this work, we did a scan of existing transformation languages. People using basically some kind of 3GL, whether it's Java or JavaScript or C# or whatever, or they're using XSLT. That seemed to be what most people were doing. And what that didn't provide was portability. I can write my mappings, and those are great languages. Sorry. Other than XSLT, those are great languages that do map for me to express my own mappings. But because the work that you do is locked into your own framework, your own architecture, you can't share the mappings in any executable sense. There's no framework for writing a single mapping and having multiple different products implement that. Even XSLT, which is the most portable of them usually, although it's a choice by the author, has architectural assumptions baked into, hard-coded into the XSLT. And what we wanted to do was to be able to share transforms between systems. It's still what we want to do. And we wanted to be able to separate the authoring and the execution of them so that you could have specialist authoring environments, because that's a very specialist tool, but then multiple systems could actually execute the mappings reliably. So we didn't want technology bindings, we didn't want context bindings. And then we looked at the existing mapping frameworks. And the two most important ones that we looked at were from the OMG, QVT and MDMI. And MDMI is a conceptually simple system that has a lot to recommend it, but whenever we've tried to use MDMI, we've fallen over because its underlying assumptions are too simplistic for healthcare data. It seems to be that for a lot of e-business stuff, it's sufficient, but the way that people trade between terminology and structure, the way that health use cases are fractal, so particularly in condition and observation space, and it may be that more recent versions of MDMI are improvement. I have still to look at that. And we're at a point where, particularly at the standards level, the lack of a good mapping framework is holding us as a community back, both as a standards and implementation community. So we set out to design a language that would solve those things. You can tell me later whether you think we have. Before I get going on the language, this is a really important concept about levels of mapping. If I've got two content models, I'm going to assume for my discussion that they're described as some kind of class model, which might be some UML diagram or some formalism that's usually based on MOF or UML meta model or something like that, but I'm using the term for today very loosely. We have a set of classes with properties and a nested graph of data. We have two of those, and we want to migrate from one form to the other. And you can write a set of mappings that I call skeletal mappings. Just enough information to tell an implementer how to understand the big picture. Right, this class maps to this class maps to this class has got this property that tells you which of these two classes it maps, and you ignore all the stuff that it's fine to leave to an implementer. Right, and I call that skeletal mapping. You just mapped the bone structure. And then the next level of mapping is I call conceptual mapping. I mapped all of the elements in the class model, and I said this concept equates to this concept. So perhaps if I'm mapping between a FHIR patient and a PID segment, which we'll look at a bit later and specifically, you might say, I say the patient name is conceptually equivalent to PID 5 in a version 2 segment. Okay, so it's conceptually equal. There's still a huge amount of work to do to turn that into an actual executable code that will do the mapping, because there's so much you haven't yet said. But it's enough to let an analyst know what the intent is at a more fine-grained level. And you can go to the next step and say, actually, what I'm going to do is I'm going to do that process all the way down to the primitive types. I'm going to actually check all the data contents, and I've pretty much mapped the domain values. And I call that detailed mappings. These are concepts, right? It's not like we have any formal categorization for this. It's just to understand the process. But then you can actually say, I'm going to set out to write executable mappings. I'm going to write the relationship between the two content models in such detail that I've accounted for every single possible domain value in the source graph of data. I've accounted for all the special cases, all the tricky rules around if this, then that, or if that over there, then... And you've accounted for all those things, and now you have an actual specification of a relationship that you can execute. You can give to an engine, and you give source data and say, here, give me some output data. So, as you might expect, the amount of information you need to provide grows as you move down this cascade. And it grows by an order of magnitude as you move down the cascade. In very simple cases where you've got not a lot of hierarchy, or no hierarchy, you've got very well understood business requirements, you've got very strictly imposed terminology boundaries, it's classic e-business. Actually, conceptual mappings is almost the same as detailed mappings, but as soon as you start getting multiple levels of hierarchy, trading between terminology and structure, which I'll show you examples of later, your complexity starts to grow exponentially. So in FHIR, we're focused on infrastructure for concept mappings and executable mappings. So let's talk about concept mappings first. There's a resource in the FHIR spec called ConceptMap. Most people, it's described in the terminology section, and its principal use is for mapping between terminologies. So terminologies are interesting because in a class model sense, they describe a set of concepts where each concept is a class that has only one instance. Okay, that's what a terminology is from a UML perspective. There's a bunch of other stuff that go with it, but that's how you look at it if you're looking at it from a UML perspective. And so we describe, you might map, for instance, between a LOINC subset and a SNOMED CT subset, and that would be a typical use. So, well, for this, I've got an element that I'm going to map. It's got a code. It's in my LOINC code. By the way, just for your convenience, here's the display for the LOINC code, because not everybody remembers every LOINC code on the top of their head. And it has these following targets in SNOMED CT. You can talk about SNOMED CT codes and say what kind of relationship they might be equivalent, or they might be wider or narrower, or they might even be, you might be asserting that they're not related. and you might make a comment about the mapping. So that's the simple mapping. And then for dealing with complicated cases, you can talk about maybe if there's another value present, we might map it differently. But for our focus here, we're just interested in a simple thing where we can say this maps to this concept. But in the same sense that we can map terminologies, we can treat FHIR resources and version 2 structures and so forth as a terminology of elements. And so each FHIR resource defines a set of concepts which we think of as a hierarchy of class, but it's actually each of those is a concept, and we can map from concept model to concept model. So here's an example of it used as a terminology. We're doing here with home address. We say here's the FHIR home address code, home address use codes for address, the 4 codes that we have, and here is their mapping to version 2. Okay, so it's a terminology use of the mapping. And we in the terminology project, or sphere of work in FHIR, we use these quite a lot, and we're gradually building them up in sophistication. And we've done a few mappings, and we clearly have to expand that. And note here, we actually claim disjointness because people often confuse these things. But then here's an example of this applied to a concept, to an actual class structure. So here's patient with all the concepts defined in the patient model, patient resource, and here's their equivalence in HL7 version 2. You can see that this is straight out of the spec. Has anyone looked at the mappings tab that this comes from? Just a few people. A lot of people write to me and say, it would be really great if I had mappings to X. And I go, well, you could look at the mappings tab, and it's there. We put a lot of work into that. Okay, so this is off the patient mapping tab. And you can see this is a conceptual map. We've said we're going to map the name to PID5, but also to PID9. And we haven't told you why you would choose either of those. But sometimes we actually make some kind of comment here. So it's very loose, right? So you can say to a person, there's enough information to get you going, which is why we provide that level of mapping. But given the variety of use of version 2, not that there's any variety of use in FHIR, given that, we can't really say much more than that. But we could take a specific case and say more. So that's the conceptual mapping framework, and it's got good, important use. But it's not enough. So we wanted to go further than that. We wanted to say that we want you to be able to write a mapping language, so you write in your mapping language and talk about merging instances, to talk about if you have an instance of data and you have to merge another instance, so how do you get that other instance? And that's one of the things that's least portable between systems. So for instance, I've got a patient message. I've got an AO8 message, and I had previously received a notification of allergy message. I want to merge in the information from the previously received allergy message into the AO8 as it goes by. That's a pretty classic transform requirement from a version 2 world. So how do you do that kind of stuff? How do you handle reorganizing structure? And also, there's a bunch of data micro-transformations. So we wanted to be able to have a language that allowed you to do that, and to do that reproducibly. And that's where we got the FHIR mapping language. So the FHIR mapping language I actually co-wrote with the architect, with the author and architect of the OMG QVT specification. One of the FHIR community participants paid for us to work together and design the language. It ended up with a very different language than what I expected. And it's a real mental transform from procedural languages to understand the FHIR mapping language. It wasn't where I thought we would end up. But it was driven by Keith, who did really great work on that. So first thing we said, we defined an API. So the API is, if you want to host the mapping language, you have to implement the API. And the API is a set of services you provide to the mapping engine, or conceptually to the author of the mapping, that does things like terminology transformations, it does getting and finding existing content, and basically it takes all the things that are system architecture specific and abstracts them out of the picture. And so that's the portability aspect. So all the things a system architect would choose, because it varies from system to system. How do you find content? How do you create new content? It needs to be identified, stored in a database somewhere probably, or have some persistent identity. How do you do that? We abstracted all that out behind an API. So the standard API that provides services to the transformation engine. And then we defined a language that uses the concept of a class structure and the API, and it describes the source to target transformation. And we defined a concrete syntax, which is the FHIR mapping language, and we also defined an abstract syntax for the concrete language, and then we turned the abstract syntax into the StructureMap resource. So because we have a hammer, it's going to be a nail. So the language, what it does is the language describes transformation from one set of instances to another where there are trees of elements. So directed acyclic graphs, technically, where each node has a name and either children, which are nodes, or a value. That's the fundamental assertion that we started with. We describe one-way transforms. We don't describe two-way transforms. In the simple case, one-way transforms and two-way transforms are the same thing. If all you're doing is you've got a set of elements and you've got the same elements on either side and the names are different, then a one-way transform's kind of meh, because you just flip them over and you get the same transformation back. When you start getting complicated things, you say, I know how to map a subset of stuff. I'm going to write the rules around the mapping of that subset, and I'll write the rules about the things I can't map, and you're trying to do that in both directions at the same time, and actually you start restructuring data. It rapidly spins way out of control really quickly. And we said, we're not going to take that problem on, because we're trying to actually maintain somehow in the language some meaningful way of having totally different hierarchies for the two different transforms. We're just going to make it separate, two different transforms. So they're all one-way transforms. The next thing about the language is the language presents a series of statements about relationships. There's no procedural element to the language at all. There's no process in the language. It's purely a statement of dependencies and relationships. You can say this mapping relationship depends on the output of another mapping relationship and create dependency relationships, but there's no aspect of do this one first and then this one and remember the variable. It's a pure statement declarative mapping language. So there's no process, and that's a kind of a two-way sword. On the one hand, sometimes it's pretty natural for us to talk about a process. Do this, remember the output, do this, grab the output from previous, we call them variables. And so sometimes it's a real head shift to move to a pure declarative language. On the other hand, it's a really powerful technique. The most powerful thing about the technique is an engine that evaluates the mapping language can evaluate the mapping language at the meta level. Say, I know the possible set of inputs, and so I can tell you the possible set of outputs. That's a really powerful technique because it means that I can take a set of known inputs, write the mappings to a FHIR resource and produce the profiles that describe the possible outputs, the possible kind of FHIR resources you'd get. And it means that you can parallelize the transform for performance. There's a bunch of advantages from saying it's purely declarative. It's just harder work for the author. Okay? So possibly the real question with the mapping language is that a good trade-off? We wanted it to be hierarchy-based where possible, so that you could do graphical designers, and there is a graphical designer that's available and works for a subset of cases. And if anybody's really interested in that, you can come and talk to me later. It's written by an English guy by the name of Robert Warden. And there's some implementation engines, and there's a bunch of people working on it. We'll see how it goes. It's modular to allow reuse, and when types are present, you can use them. So I'm going to explain that. I'll come back and explain that then. Okay, so that's sort of the design parameters of the language itself. And then we have the resource StructureMap, which contains a module of the FHIR mapping language. And its defined content is actually the abstract syntax tree. and there's tools that can interconvert between the forms. So technically when we talk about FHIR mapping language, we store and exchange the modules is StructureMap resources, and that's how they're published through the FHIR specification. So I'm not going to get that far into this tutorial, but I'm going to give you a sense of how the language works. So I'm not going to talk about FHIR resources. I'm just going to talk about general generic trees. So on the left I have this structure which is named left, and it's got a string it's got A, which is a string. And on the right we've got A, which is a string. This is like pretty much a null transform, right? It's the simplest case you can imagine. And so we want to take left and convert it to right. And from a mapping language point of view, we're not really actually doing anything, but this is about just setting up the framework. But before I go on, I want to talk about the content models here. So this diagram, which some of you might recognize, is taken out of the FHIR path specification. And it says that this is what we're dealing with. We're dealing with a tree of data, a directed acyclic graph, where each element has a name, each node has a name, and it has a type. And it has, some of them have values or they have sub-elements, so it could be both. So that's our working assumption about these input and output trees, and that we're going to work with those trees. And that means that the engine that actually does the mapping has to know how to do that part of access the tree. And the author, who's actually writing the mapping statements, has to know how the engine will access, or how it looks when the engine accesses the tree. So you need to know the input and output models. And so how that works technically with all the implementations we've got is they all implement the FHIR path interface, which is a meta interface onto the classes. So you feed, as a host application, you take the content you want to transform and you give it to the engine, but you give it to the engine as an interface, which is an interface to a navigational structure that says, well, what's your name? What's the name of your children? Give me a child by name. What's the type of the child? What's its cardinality? And so we use that same interface internally for the FHIR path engine and for the mapping engine and for the graph definition. There's a bunch of places we use that interface in the tools. So that means in order to support the language, to use the language, you have to actually write an implementation that feeds the object class, whether it's a version 2 message or a CDA wrapper or whatever, to feed that into the engine. And so a programmer has to do that. But then we wrote a generic interface that actually says, well, I don't know anything about anything, but if you give me a structure definition, a FHIR structure definition, now I know how to read content. I know how, I've got a description for it. So if you write a FHIR structure definition description of the content, and I'll come back to a good example of this later, now you can feed it into your transform engine. And I'll show you an example for CDA later. Okay, so go back to our example then. We're going to convert from A to A, so it's really not very much. So this is about framing. We're just going to set up our language and say we're going to map from one source material to the other, and they have arbitrary URLs I assigned for this tutorial. Then we say we're going to have a group of mappings that take as an input source and target. So in this case, the engine says to the application, if you want to run this map, you have to give me two objects, the source material and the target that you want it to go into. You can set it up so that the host only provides a source and gets a target back, but in this case we've said, the host, you give me a source and a target and I'll know how to do the mapping, so here's the rules that we're going to write. So this is just framing. Now the rule is really simple. For any source A, make a target A. That's as simple as we can get. In fact, there's a simpler form where you don't need the A structures here, which just provide continuity once you've got more than one thing in play. So just for source A, make target A. Now, if the names start changing, we can say for source A, make target A2. So if the names are different. And so this is not procedural. We're saying if you find a source A1, then you would make a target A2. Then we start throwing extra things like, what do we do if there's a length restriction on one side or the other? How do we handle that? And there's a set of choices for saying what we're going to do. And one thing I wanted to point out is you say, you can say, well, we're just going to truncate it to 20 characters. Or you can say in the language, actually, if it's less than 20 characters, then we'll handle it. So you can put a condition on your mapping clause and say, this mapping clause only applies in this condition, and the condition here is a FHIR pass statement. Or you can say, check that the length is less than 20, and if it's not, fail with an error message. Right? The mapping as a whole fails because we don't know how to proceed in that condition. So I'm going to skip some of this because this is straight out of the tutorial in the FHIR spec. So you're all welcome to read the tutorial and make suggestions for improvements. But we can start dealing with more complicated. I've jumped a few things, but here is a classic example of restructuring. What I'm going to do is I've got, on the left-hand side, I've got a string, an E, which is 0 or more strings, and F, which is a string. And you'll find this all the way through HL7 specs. And on the other side, I've got a repeating structure where each string has a code. And so this has been pushed down into here and it's going to repeat on this side. So if we actually reverse this, we'd be going, hang on, what if they're different? But for this way, we don't have to worry about that. And so this is a fairly typical mapping task. So in this case, you say for each E in the source, make a E in the target, and in the E in the target, I jumped something in my head when I was doing this. So what we want to say is that if, I should have reviewed this slide before I decided to talk about it, shouldn't I? Okay, that's it. So the first string, this is what the rule is. The first string has a code which is F, and the others have a fixed code. This might be like first name, second name, right? Given names. The first given name is considered special. And so when we produce on the right-hand side structure, what we want to do is produce a different code for the first repeat and then use the fixed code for the other repeats, which would be like middle names, for instance. So here we say, for source, E, for the first E, okay, make an E, which is a complex structure, and then in that, for each source E, make an F with the value of the E and give a fixed value. And then for F, we create that and we put it in first in the list up here, and we give it the same value as the F, but we give it a different fixed value code. So you can see the language starting to get complicated as you start to approach complicated cases. And then you can see how to restructure the code. So I'm going to stop now with the tutorial because that is just a tutorial in the spec, and start talking about how you use the mapping language and some examples. So we provide a Java command line that will do the transformation. So you can use the command, the validator actually, the FHIR validator will also run transforms, set of command line input to run the transforms. And so you see that blog post, and that describes how you do that. I think it's still valid, and it's on my list of things to do before I did this presentation to check, but people keep talking to me. And you can also post to the test.fire.org server. You can set up a structure map, put it on the server, and then post content as long as it's defined by a structure map, structure definition. So I'll come back to that in a second. The other easier way to invoke the transform is to download the toolkit, the FHIR toolkit from my website, which is link to from the wiki. And you can specify the source data you want to transform, the destination. That can be a URL or a file. The URL of the module that's going to execute the mapping. It will perform the mapping, produce the traces here, and then save the file unless it fails. And at the moment, that's the error, is you haven't installed the validator. But and then you can specify your package dependencies here. So that's your definitions and your mapping library and so forth. That's the easiest way to run the validator. Now, let's talk about some examples. How many people have seen, let's see, this page in the FHIR specification? It's down here. So on this main documentation page, there's a page here, transformations between DSTU and DSTU3. How many people have seen this page? Hey, more than I thought. Good. All right. So this page is the summary page for the transforms between release 2 and release 3, which are all written in the mapping language. So there's plenty of examples to look at. And so for each resource, I went through every single resource in the spec. It took me a month. And I said, some of them didn't exist in the release 2 spec, or some of them have just been changed so much I'm not even going to try and write a transform. But others I went through and said, okay, I'm going to actually write the transform that transforms from release 2 to release 3 and back. And then I wrote a little test engine that goes through and executes the transforms and all the examples in the specification. And when I get the release, so I convert the release 2 example to release 3, I'll validate against release 2, and then I round trip it back to release 2 and test to see whether it round tripped perfectly or not. And this table summarizes the outcome of the performance of the mappings. So you can see that there's still plenty of work to be done. And some people have actually picked up these mappings and then taken them into production. We're going to have a look at a particular mapping, which is the patient mapping. So this is from the patient page, R2 conversions. So you can see that we're setting up the R2 patient and R3 patient, importing all of the conversion maps, and then working through the map. Most of these are null statements, right? We haven't changed the name of the attributes, but there's a couple where we have one of those was one. Anyway, so there's most of the resources have these. Some of them are pretty tricky, so we'll just look quickly at this one. With the value set resource, we actually pulled out a piece of the value set and put it in a different resource. So with the value set, I'll move it up the screen a little bit. With the value set code system, we actually, when we find a code system in a value set, we create a code system resource and then go off and populate this other resource. So it's splitting the content up. I'm not going to go through any more details of the fine details of those, but this page summarizes the performance of the maps. Okay. Now, at the moment, we're working on CDA to FHIR transforms. So if you've gone to other presentations here, you'll know that there's a bunch of tools out there that will do some aspect of FHIR to CCDA conversion. And that's great, and we're really happy that those tools exist, but it's raised a challenge to us, which is, do we know that they're doing the conversions right for a given meaning of whatever that would mean? And in particular, and more generally, HL7 has been asked to go on record about the transformation. So we have a project at the moment to work up the transforms with the FHIR mapping language. And why we would use the FHIR mapping language in particular is that we want to have portable mappings for CCDA to FHIR. If people have gone ahead and implemented the FHIR mapping language, then they could go and implement that straight into their system. And a few people have. Alternatively, because the mappings are purely declarative, we could generate CCDA profiles automatically. And also, because the mappings are purely declarative, you can translate. You could write a translator to translate from FHIR mapping language to XSLT. And that's how Robert Warden still works. So because it's purely declarative, it's the right place to start with. So what we have is a set of CDA definitions. CDA definitions define CDA itself, and you might find that interesting. So they're published on the build FHIR server at the moment. So this, and the link's in my slide. So this is actually a formal definition of CDA as a, let me find out what I'm doing here. It's a bit rough. For instance, you'll notice that this list of names is not alphabetically sorted. That would probably be useful, so it's kind of rough at the moment. So here's the clinical document definition. And for those of you who know and love CDA so much, you'll recognize this structure. Right? This is the CDA structure that define, that is defined in the CDA specification. So given this structure, this set of structure definitions, Rick, sitting down the back making trouble, Rick put me up to actually generating a schema for CDA from those structure definitions, and I've got it working now. There's no hacks anymore. Okay, so I can generate a CDA schema that almost completely works for CDA. It's actually a much simpler schema than the existing CDA schema, because we're focused not on trying to represent semantics, we're just purely getting structure defined. The FHIR validator can read and validate CDA documents against the CDA definitions. Not a transform of the CDA document to FHIR, but we can actually validate CDA documents directly. And potentially, if someone was to take this form, if someone was to take this output and actually show some genuine many hours of love to it, we could potentially publish the CDA spec this way. It's theoretically possible. The CDA people have to decide whether they want to do that or not, but it's possible. This is where I want to go. And so now we're working on formally endorsed mappings between CCDA and FHIR. So I'll just very quickly show you. Here's the map that we're currently working on. It's not yet public, but it should be, and we were working on making it. So, the one hassle with this useless keyboard on this Mac is that these Windows shortcut keys don't work so well. Okay, so one more. All right. So here we're setting up our mappings. We're mapping from CDA to FHIR. So we're setting up all our dependency mappings and our aliases, and then we'll say, we take as a mapping a clinical document, CDA document, and we have as a target a bundle. So if you want to run this transform in your engine, you've got to say, here's the bundle I want you to populate from this clinical for CDA document. And you'll see the CDA, the source ID becomes the bundle identifier. And it is an implicit type-based transformation which we have in the background, which says, well, hey, source ID is an II data type in CDA, and it's an identifier type in FHIR, and so I'll go off and find the designated transform for that type-to-type transformation. And so we don't need to say that here, it's taken for granted. We will fix the target type of the bundle to document. And then we start working through the actual clinical document content. Template ID, language code becomes the bundle language. The set ID becomes the target identifier of the bundle. I hadn't seen that before, Rick. We'll have to look at that. So then we're just working through the CDA content, mapping it, patient, record target, mapping it to the bundle, the composition in the bundle, and just walking through the document. It's still work in progress. It's couple of bugs in the tooling that Jean, who's doing the work, found, and I have to work on the bugs. I was supposed to do it last night, but we had too much fun last night. So that's work in progress, and that should be published soonish, but it will be very draft. And that will be the formal expression of HL7's view of what the correct relationship between CCDA and FHIR is. Okay, one more example I want to show you, and then I'll take questions. So this is an implementation guide I was working on for CAP, RCPA in Australia, the equivalent of CAP. It describes a very comprehensive report for a cancer protocol, 200 or 300 elements for reporting on, say, a colorectal report. So what we did was we wrote just a structure in FHIR that was a statement of what they thought they said. And then we spent months arguing with them about what they actually said. And so this has got nothing to do with, this is not about FHIR, this is about what they said. They said that a colorectal report has a pre-analytic section which has clinical information, operating surgeon details, etc. We just figured out what that would mean for an element in FHIR and then put it in a structure that said what they said. And then what we did was we wrote a mapping in the mapping language that mapped from that structure to a set of FHIR resources, mostly observations in this case, but some patient, practitioner, procedure report resources. And then, out of that, I took some examples that they had provided. We wrote the examples in their syntax, and then I used the mapping language to create examples. These are all bundles, and they're very long. Well, this one's not long, but usually they are. So that's the generated examples. And also, I generated profiles. So, let me go back one. So you can see that this is the backbone, the graph definition for the logical model. And each of these is a profile that describes, is a profile on observation that says which bits of observation are in use or not. This was all automatically determined by the mapping language, what was possible inputs to what was possible outputs. So that's where we are with the mapping language. I'm going to stop there. Thank you for coming and listening. The mapping language is not an easy step, right? It's much easier to simply do a conceptual level mapping. This to this to this to this. We got the structure for doing that, for exchanging that. That's easy. That's easy for people to get their heads around, but it's only for humans. If you want to do machine transforms, you've got a much bigger step to walk up, and that's what we're working on. If you're interested in the mapping language, and you want to cut your teeth on it, I have a project for the next few weeks that I want people to work on the mapping language. I've got a few volunteers. If you're interested, come and volunteer for writing. This is actually for writing R3 to R4 transforms. Okay, and I'll stop, and I've probably used up all the time, but any questions if until we get kicked out, because it's morning tea time. This was here. See, actually, you can't just enter a mapping transform here. That'd be a good idea. I should do that. Is that what you mean?
You put StructureMap in here, but it's easy to use a script.
That's just the URL. But if you really make that script, yeah, I could do that. Any other questions? All right, thanks, everybody.